All right, let's talk about a breakthrough that isn't just about faster computers. This is something else entirely. We're talking about a fundamental shift in how we understand reality itself. So yeah, you're going to want to buckle up for this one. Go ahead, mark your calendars, because if the source material we're digging into today is right, this is the day Google finally did what so many people thought was impossible. They achieved verifiable quantum advantage. And trust me, it's about a whole lot more than just building a better machine. And no, that is not an exaggeration. Google's Willow quantum chip didn't just chew through a problem that would take a normal supercomputer literally longer than the age of the universe to solve. It actually did something that, until right now, we all believed was physically impossible. So what exactly broke? Well, we're talking about a core principle of thermodynamics. A rule that's been in the physics textbooks for 2 centuries, governing everything from the first steam engines to the processor and the device you're watching this on right now. For 200 years, the Carnot principle basically set the universe's speed limit for energy efficiency. Think of it like this. There was a hard and fast rule about how much performance you could get out of any engine. Well, that rulebook just got ripped to shreds. Because at the quantum level, scientists have now proven it's possible to smash right through those limits we thought were unbreakable. And just to give you a sense of this sheer scale here, Google's Willow chip ran 1 trillion measurements in a matter of weeks. That's more measurements than every other quantum computer in history has ever performed combined. It's that kind of brute computational force that made this whole thing possible. That's the feeling that's just rippling through the scientific world right now. This isn't just some great piece of engineering. It's a discovery about the universe itself. It feels like we've just found a door to a whole new level of reality we never knew was there. So, how in the world did we get here? Well, it wasn't just one single eureka moment. It was more like a perfect storm, a convergence of 3 separate breakthroughs that have finally hit their tipping point all at once. Okay, let's break these down. First, quantum computers finally figured out how to fix their own mistakes on the fly, which made them stable. Second, they took that new stable power and pointed it at a huge real-world problem, simulating complex molecules. And third, and this is the one that really bends your brain, they figured out how to tap into a completely new source of energy from the quantum realm, which is how they broke that old law of physics. Now, this first step, this is the absolute game changer. See, quantum states are ridiculously fragile. A single stray particle could throw off an entire calculation. But quantum error correction means the system is now robust enough to do actual, useful work. This is the moment quantum computing basically grew up. I love this analogy because it really gets across just how wild this is. Imagine trying to build a car that's so complex, moving so incredibly fast, that it can find and fix its own problems in real time without ever hitting the brakes. That's exactly what's happening, but on an atomic scale. And the level of precision we're talking about is just staggering. We're at 99.97% accuracy. That means only one tiny error for every 10,000 operations, all happening in nanoseconds. That's the kind of reliability that takes something from being a cool science experiment to a tool that can actually change the world. Okay, so now that these machines are finally stable, this technology is getting ready to leap out of the physics lab and crash right into our everyday lives. It's about to completely revolutionize entire industries. Just think about it for a second. Developing new drugs could go from taking a decade to just a few months. We could design brand new materials that don't even exist in nature, like room temperature superconductors. We could create financial models and climate models that are actually predictive. The ceiling on what's possible in these fields just got blown wide open. You have to understand, the difference between a classical computer and a quantum computer isn't just a gap, it's a chasm. And that chasm is getting wider, exponentially, every single day. And this, right here, this is the mind-bending part. We are now solving problems in a few hours that would take the most powerful supercomputers on Earth millions of years to even try. This isn't a 10% improvement or a 2x speedup. This is a totally different category of power. And look, this isn't science fiction set in some distant future. The roadmap is incredibly aggressive. This year is all about verification. In just 2 years, we're expecting fault-tolerant systems. By 2028, you'll see commercial quantum services become available. This is happening right now in this decade. But of course, with any technology this powerful, we have to talk about the other side of the coin. There's immense promise, yes, but there's also an immense amount of peril. We may have just created both our most powerful tool
and our most dangerous weapon.
I mean, think about it. The same power that can simulate a molecule to cure Alzheimer's could also be used to design a new bioweapon. The systems that could create a perfectly efficient clean energy grid could also shatter the encryption that protects our entire global financial system.
And that's why this has kicked off a frantic race. It's a global race to upgrade all of our security to new quantum-proof standards before these machines get powerful enough to make our entire digital world vulnerable.
Which brings us to the final and maybe most important takeaway from all this. The real revolution isn't just in the silicon, it's in our way of thinking. The future won't belong to people who just use quantum computers. It'll belong to the people who can grasp the weird, counterintuitive logic of the quantum world, things like superposition and entanglement, and use those not as problems, but as features. So the real question is, are you ready to make that leap?